Brian, who's going to talk to us about efficiency, if I remember well from the original title. But yeah, off to you. I'm also quite intrigued by this non-other affiliation.
Thank you. So, well, it's a tough presentation to follow, but I will try. It's really a pleasure to be here and learn about uncertainty quantification, which is something that I'm really interested in. Thank you. I had originally done some preliminary uncertainty quantification on this model, but I was really unhappy with it, and so I viewed this conference as more of an opportunity for learning. So I'm billed as being from nowhere or other. I want to assure you, I actually am from somewhere. Where I'm from is the University of Nebraska Medical Center currently, and probably at this point you're trying to remember where Nebraska is. So it's sometimes called nowhere, which means that probably none other is just fine. So I always have this diagram of the heart. I won't really talk much about the diagram because you all know the heart pretty well, I'm sure. In terms of a research outline, first I'll talk a little bit about my research focus and the research focus of the lab I work in. Then I'll talk a bit about the construction of what I call a characteristic deformation mode left ventricle model, talk a little bit about the geometry and so forth. Really what I want to do with this model is less about having a really complicated model. Really what I want to do with this is to estimate parameters for sort of mechanical properties and contractility of the heart. And so I struggle with modeling and seeing where the model actually hits the reality. So I'll start with a very simple example of a silicone rubber model. And then I'll move on to an in vivo quantification. And I'm only working with the left ventricle here. So this will all be about the left ventricle. And then I'll conclude with some discussion of the error sources and what I think are important ways to do uncertainty quantification on those. So in terms of research objectives, I really love this idea of patient-specific models. I think it's a really cool idea. I think there are a lot of really interesting directions that that's going to go. Also, in sort of a more classical way, I'm interested in looking at heart failure and trying to understand how different mechanisms interact, in particular in heart failure and preserved ejection fraction, which is a case where you don't have something like an infarct. So, of course, in the first topic, you're all probably pretty familiar with this sort of workflow for constructing models. You start with your imaging data, maybe some MRI, maybe some echo imaging. You do some image analysis on that. You reconstruct a kinematic model, so just the deformation. Maybe you have some pressure data that you're taking from a catheterization. You do some parameter fitting, and all I've shown here is a bunch of equations that you fit into a dynamic model of the ventricle. And so this is sort of be the process that I'll go through. So in terms of the construction of the model, I'm using sort of a reduced method. A good way to start with the reduced method is in prolate spheroidal coordinates. If you're not familiar with prolate spheroidal coordinates, you can think of them as spherical coordinates, but elongated, because prolate actually means elongated. So they're really just like spherical coordinates that have been stretched out. Of course, you stretch out a spherical thing, you get an elliptical thing. Once you have your coordinate system, the model is constructed by creating a geometry. I use surfaces in the prolate spheroidal coordinate system. Those surfaces are in the coordinate mu. Mu is really like the radial coordinate in prolate spheroidal coordinates. And just something like a bicubic spline definition is perfectly satisfactory for constructing the walls. So in terms of how this is different from sort of more normal modeling approaches like finite element method, is rather than do the full local displacements on the elements, instead I'm going to assign global deformation modes over the whole myocardium and then add in as many modes as we think are necessary. These deformation modes assume myocardial incompressibility as a simplifying assumption. Of course, we know the myocardium is not actually incompressible, but for a reduced model, this is a pretty good assumption. So each deformation mode, denoted QI, sends you to a specific shape. For example, the first deformation mode is just uniform expansion. Another deformation mode would be uniform shortening. The third one would be uniform twist. And then after that, you can get any kind of deformation mode that you want and put it in there, depending on what you think is best. In this case, this is like a non-symmetric version where the septum doesn't really deform, but the lateral wall expands. So, of course, the question when you make a model like this is, what's the best modes? How physically relevant are these modes? How many modes do you need? So I did a little bit of an evaluation of the modes that I used. And so I took some tagged MRI data, reconstructed the motion through image registration, and then I tried to see how well the modes I was using could recapitulate that data. And so the deformation that you account for with just about 5 modes, maybe 6 modes, is somewhere upwards of about 70% in the case of dilated cardiomyopathy. In a normal case, it's upwards of 80. As you increase the number of modes, you do better than this. And then, of course, the question comes, how do you make these modes? These modes are pretty just ad hoc or thrown in. Really, the best way to create the modes would be to drive them by a mechanical model like an FEM model, or to drive them by a large imaging database like the Cardiac Atlas. I don't have this yet, but I will in the future. But hopefully this shows you that even with some pretty basic modes that are constructed here, you can get pretty good agreement with sort of normal cases of cardiac function and dysfunction. So once you have your kinematic model, you need to drive it. And of course, the driver for the kinematic model are the variational equations. And so this construction is really similar to what you would have in a normal finite element model. In fact, it's essentially the same thing. You have a passive elasticity. You have some tissue viscosity. You have a parameter for active force generation, or rather a stress term. And then you have the surface tractions at the endocardium. I'm using the commonly used, or the sort of classical strain energy function, which is this sort of Fung type model, which has 4 parameters. This is not the Hosoffel-Ogden model. Of course, this could be constructed with that model. I know that it's improved. The invariant-based models are indeed better. In terms of what I'm trying to do here, I want to use something simple, so I've just stuck with the 4-parameter model, because even 4 parameters is really hard to identify. So what's the output of this? So here's a simulation of the cardiac cycle for the left ventricle, producing sort of a standard PV loop. The advantage of using this type of simulation, of course, is that it's fast. This one takes about 9 seconds to compute a cardiac cycle on my desktop machine, which has 18 cores. And it uses about 23 deformation modes to drive the kinematics. OK, so that's the model buildup. There's still, I think, some work that would be interesting to do on that model and some various validations. Now, I didn't really want to validate it against a different modeling technique. My interest is really in what can this tell me about the in vivo data? Can it give me any interesting information about what's going on with the person's heart? So the thing I started with was a really simple model of a left ventricle that what we did was we took some MRI data, we printed a mold, we poured silicone rubber into it, and then extracted the model and then inflated the model. The model is made of silicone rubber, so it's purely elastic. That means it can be described by the Mooney-Rivlin, which was talked about in the last talk, for just a simple rubber model. And so I wanted to also see, OK, basically, how much experimental error am I seeing as well? So I used some echo in order to evaluate what the stiffness was. And so I evaluated the stiffness of this thing in 2 ways. First, tried to get the stiffness just from the imaging data together with the pressures collected. And then second, just mechanically tested the material to see what kind of material parameters you get from the mechanical testing. So these are the responses that you get from this. So the response A is when you estimate it by a mechanical testing. And so this is just sort of the truth. The gray area around A is 1 standard deviation from across like 10 samples that we mechanically tested. B is the stress-strain response if you use the 3D echo shape and displacement to estimate what the response of the material is. And then in C, instead of using the 3D echo to estimate the shape and the displacement, I use the 3D echo to give you the displacement, but started with the actual true shape of the model. What this shows is that initially the response was outside the range of the mechanically tested responses, so B was pretty far out. But once you give the true shape, you get better agreement. So where does this error come from? This error really comes from the fact that when you estimate the shape from 3D echo, the size of the myocardial wall is about 30% different than the true thickness of the myocardial wall, which creates a big error. I recently saw a paper on uncertainty quantification of myocardial wall thickness by FEM modeling, and I think that showed the point very nicely that if you can't measure accurately how thick your wall is from your imaging technique, you can get really big errors in your estimations. And so if you're using different techniques like 3D echo versus MRI or these types of things, you really have to be careful with how much error you're getting from your measurements. Okay, so that's sort of the benchmark case, which I wanted to understand whether or not the model could actually give me estimates even in an isotropic case. So here's another case. This is some data from a control animal in a pig study of heart failure. So we take MRI images, and then we also take pressure volume measurements. So these are the PV loops. The heart is a little bit smaller than a human at this like 6-month-old pig. And after dobutamine, you can get some different responses. You can do some different measurements. So in terms of the workflow for quantifying the cardiac cycle, first you have to do some segmentation. We use like a manually assisted segmentation where you point out fiducial markers and then it creates a surface. Then we use automated deformation image registration. And once you do your image registration, you estimate your stiffness parameters using some type of optimization method. In this case, you have to also estimate the reference shape. So as you're estimating what the inflated shapes are in your optimization, you also have to adjust your reference shape so that you can capture what's going on all the way through. So we use a mode to adjust the reference shape. And then you estimate the stiffness. Then in order to compare the estimates I was getting from the in vivo characterization of the stiffness, we also did mechanical testing of the tissue. So in this case, you have to do things like arrest the heart with cardioplegic solution and align the fiber angles. And it's sort of a mess, but at the end of the day, you can get some parameters for what the stiffness of the ventricular tissue is. It's important to note that even this type of testing has a lot of error sources in it. Okay, so here I'll get to sort of the punchline if I can. So what happened when you estimate these parameters by mechanical testing? You see the values here, 0.15, 29, 13. If you use the in vivo model to estimate these parameters, you get wildly different numbers, 1.4, 2.6, 2.0, 2.8. So if you're familiar at all with the literature on estimating these types of parameters, you won't be surprised by this. You get a lot of different numbers in the literature on these. So what's going on here, and why are these numbers so different? So the reason that these numbers are so different is that when you do the mechanical testing, you're able to stretch it as far as you want until the tissue breaks or starts to soften too much. When you do the estimates from your in vivo model, the heart's only inflating as much as it's inflating, and that's all of the data that you get. So what ends up happening is your mechanical testing, you capture this exponential range, whereas when you do it with the model, you don't capture the exponential part of the curve. But if you zoom in on this area up to about 10% stretch, the response, which is in black from the in vivo model estimates, are actually quite similar to what you get from the mechanical testing up to 10% stretch. But after that range, your response is quite a bit different. So what do these differences in estimates mean in terms of cardiac function, which is really what we're interested in, is how to relate these stiffness estimates to the function so that you can make some kind of informed decision for how well the person's heart is working. So in this graph, I've shown A, which were the pressure volume catheter measurements. B was the quantification of the cardiac cycle using this model, using the shape and geometry, as well as the pressure measurements. We tried to fit the contractility to the end systolic part of the pressure volume curve, and then this part fits the diastolic stiffness parameters. To generate C, took exactly the same stiffness parameters, exactly the same simulation as B, but with the stiffness parameters that were used in the mechanical testing. So what does this show? Regardless of which material parameters you use, you get basically the same properties. And this is because these amounts of stretch we're getting are mostly in the linear region of stretch. So you don't have some really large stretches. So you're really on the stress-strain curve, probably somewhere like 15% or less. So in that region, you don't see a lot of difference. But what happens if you now take your simulated ventricle and you start to fill it more, so you increase the filling pressures? So in this case, you double the filling pressures from 3.5 millimeters of mercury to 7 millimeters of mercury. So in D, it used the simulation where you have the stiffness parameters from the in vivo data, where it wasn't as stiff in that later, higher stretch region. And in E, you use the same model, but with the stiffness estimates from the mechanical testing. So what you end up seeing is that if you just push past this region where you had good agreement, your parameters from the mechanical testing suggest that you will barely fill anymore, whereas the in vivo estimates say that you'll keep filling a whole bunch. I do think that these stiffness estimates from the mechanical testing are probably a little too stiff, just like the ones from the in vivo in that region are not nearly stiff enough. So what are the conclusions? You can use this model to estimate stiffness. I think that much in general is true. Whether or not you can differentiate between different directions is another question. It shows that your estimates are very sensitive to your measurement error, and I don't think that this is considered very much in a lot of modeling papers where there's this type of quantification going on from things like echo data. The limitations in the range and quality of the in vivo data really limits the parameter identifiability, even though you probably get your linear stiffness pretty well by fitting the data. So you really have to be aware of what your limits are in terms of the in vivo data. Another thing is that even if your parameters are really different, it may not make much of a difference if you have a lot of trade-off between parameters in terms of the function or in terms of what your measurements are. So that's a big issue. If you fill a little bit more to higher pressures, those differences really start to matter. So, of course, the sources of error, limitations of the imaging method. I think we've heard most of these at this point. Insufficiency of the data to fully characterize the mechanical system. One of them that I don't feel like is addressed enough is the fact that from most in vivo data, you don't have pressure measurements. And this is a huge issue because if you don't have your pressure measurements, all of your stresses are scaled off. And then simplifications to the mathematical model. How much error are you getting when you use this type of deformation model versus you use a finite element model in terms of your eventual outputs, which are the stiffness estimates. So in terms of what I want to do for uncertainty quantification, and I'd be interested, I have a poster if anyone wants to come talk to me about ideas for this, is rather than quantify the uncertainty in the parameter estimates, quantify the uncertainty in the responses. So I'm not exactly sure what's a good way to do that. The responses are dependent on a lot of different things, but I feel like just quantifying the uncertainty of the parameters, you get these huge ranges for your parameters that aren't really meaningful. And so if you tell people, well, you have this giant range of your parameters, they're not going to be interested in that, and it's not going to say anything to them. So you need a better way to understand what the stiffness is than just those parameters in these sort of standard models. Also, I would like to quantify the uncertainty based on whether or not you can recognize that exponential response. So is there a way to say, OK, I did capture the exponential response. So that's when the collagen kicks in. Or no, I did not capture the exponential response. And then finally, to look at the fiber angle variability and its implications on LV functional quantities. So you don't have an estimate for the fiber angles in most data. So if you just estimate the fiber angles, how much is that going to affect what your ventricle is doing? And if anybody has any references for that, I'd be interested to see them. And with that, I'll end, and thank you for your attention.
Great. Questions from the audience?
Yeah.
It's a wonderful model. I have two questions. First question, how do you select stress-free geometry in MRI?
Yeah, so the stress-free geometry is not given. In our data, it was pretty close to the stress-free case because it was like 0.8 millimeters of mercury at the beginning. But what we did is we readjusted the shape, starting with the shape that we measured at 0.8 millimeters of mercury, or in another case, it was like 5 millimeters of mercury. And then we gave it a mode to adjust the size of the cavity down so that when it inflated, it would inflate to the shape at 0.8 millimeters of mercury. So there's actually an extra couple parameters in there that define how you go from your unstressed shape up to this shape. Then you optimize that at the same time as your stiffness parameters because they're connected.
Second question, quadrature rule. How do you choose quadrature rule? Does it depend on number of modes?
Yes. So the rule that you use in this geometry is pretty simple because you can just integrate in all of your prolate spheroidal directions. And so just like a second order method, and then the number of points that you use to integrate depends on how many modes you have. So as you increase the number of modes, you have to include more integration points.
So I want to get into the fiber angles and the pressure. So how do you do that at the moment? So using the pressure as a literature value fixed from the literature, or are you taking that as a parameter that you infer? And for the fiber angles, what do you use? Is it a rule-based method or sort of an agent-based method to set the fibers and then infer the parameters as well? Or?
Yeah, so with the fibers it's harder. With the pressures in this data was easier because we have pressure data because this was invasively measured. For the fibers, we use sort of standard values like 60 to minus 60, this type of thing. I was going through some uncertainty quantification of, well, what happens to these parameters if you adjust your fiber angles, and what happens to your fit of the data. And what it was showing me was that when you adjust them, you create errors, and you get different parameter estimates. But I was still not sure what the best way to go through that quantification of how these fiber angles are affecting your measurements. So, I mean, right now it's just based on the literature values, essentially.
Myself, it's a field of research that I'm quite familiar with, and I will have a couple of questions myself as well. The first one is that I quite liked it how you explain the lack of identifiability between the linear and exponential terms. And all your questions about we work in the linear range is quite true. In the usual heartbeat, we don't get so much into the nonlinear regime. So we need some tricks to solve that coupling. The first thing is that the coupling you saw in your data, it's all a scale factor between how much is in the linear, how much in the exponential. If you look at the product between those two, that's roughly constant.
Yep.
So that's something that we saw some time ago. But then to break that identifiability, you can break tricks. And some of those tricks is to, for example, look at ratios of how much work and energy has been done and stored in the myocardium, something I've published about. And you can find the exponential term getting rid of the linear one due to how the constitutive law is like. So with that, with the same observations, but changing the cost function, you can break the interferability. So that's a trick that you can play with. And then it comes to the question of, that's the comment of, or maybe the license of knowing a bit of the field and complementing the presentation. The question comes in terms of uncertainty. One of the main sources here is the stress-free configuration. We already touched on that. And I would like still to push you a bit harder into how one single mode was able to account for that. You have in your heartbeat, you will never have that stress-free configuration. And that is the rest. And that's going to affect everything. So if you can develop some more thoughts about why that mode was designed and how that mode was designed, and how that list of up to 40 modes I think you had at some stage. You said that you had learned from imaging data, and then did you do a principal component analysis of those modes or that data? Or can you comment more on how you end up in 40 modes and how you select the modes you need to do to deflate and get that reference configuration?
Yeah, so the number of modes that you use and the way that we designed them is still pretty basic. Didn't use a lot of imaging data, but we want to use like a principal component analysis, like they did with the cardiac atlas, to get the actual driving modes. I think that would help to improve
then how
the overall.
If I follow well in your presentation, you had up to 40 modes. How do you define up to 40 modes a priori conceptually?
So those are just designed based on some natural basis functions, like Fourier basis functions in the circumferential direction, and some cubic type functions in the, or rather some reduced Fourier functions in the opposite direction. So you just use some different standard bases, and it actually gives you like a pretty reasonable estimate for the deformation on those ones. And you're right, in terms of the unstressed mode, you're absolutely right. It's a really hard problem, because if you add in a whole bunch of parameters to reshape your reference shape so that it inflates to the right thing, then you're sort of complicating the problem by many factors, because you only have like 4 stiffness parameters. Now you got like a whole bunch of parameters for what the reference shape is going to look like. So you want to use as many as you need to in order to sort of recapitulate that particular model. So for this model, you probably wouldn't need that many in order to make it inflate to the shapes that you're seeing. Whereas if you have a more complicated deformation model, you're going to need more. Now the issue is, of course, that then you're not accurately capturing the changes in shape as well as you would if you had all of those additional degrees of freedom. So more of what I'm trying to do with this is, rather than accurately capture all of the deformations that you're seeing, is capture as much deformation as you need to get good estimates for the stiffness parameters quickly. And so really the validation to me is trying to validate it against sort of the mechanical testing and the experimental values that you get, and see whether or not you can recapitulate sort of the same kind of stress-strain patterns using it without necessarily capturing absolutely all of the motion.
We need 3 minutes, Richard, to one last clap for